Okay, so we've had a look at the remainder theorem. Now we're going to have a look at our next theorem, which is called the factor theorem. We're going to have a look at it in a similar way. We'll have a look at what it means, how to prove it, and then a couple of examples. All right, so the factor theorem states that for any polynomial p of x, so we've been dealing with this language for a while, so just labeling a polynomial p of x, k is a zero of p of x if and only if, so this arrow here, we may or may not have seen this before. This little double arrow here means if and only if x minus k is a factor. So the double arrow means it goes kind of both ways. So if one is true, the other is true, and vice versa. All right. So k is a zero of p of x if and only if x take k is a factor of p of x. All right. So a bit wordy. We'll have a look at what that looks like in practice, and also the proof. So to prove this, we've got to use a couple of things that we have already used previously, and some things that we might have used a long time ago in the past. So let's do it. So k is a zero of p of x. I might actually just drop this down and you'll see why in a second. So k is a zero of p of x if and only if p of k equals 0. All right, so it's just if we substitute k in, we get that equal to 0. The reason for that is a definition of a 0. So if we substitute that number in there, we should get 0. That's by definition. Also, if and only if the remainder r equals 0, and that's by the remainder theorem. If and only if p of x equals q of x multiplied by x minus k. All right, so we know the remainder equals 0, so we're just left with that. And that is the division algorithm. So we've seen all of these recently. And also if and only if x minus k is a factor of p of x. All right, now the reason for that is because that's the definition of a factor. All right, now as a student, when I saw this kind of stuff, I was like, what does that mean? So that's why we'll have a look at an example, but that's a quick little proof of the factor theorem. All right, so the first thing we're going to do is have a look at this example. So find k, given that x minus 2 is a factor of x cubed plus kx squared minus 3x plus 6. Hence, fully factorize that same polynomial to the power of 3. So what we know is, well, firstly, let's let p of x equal x cubed plus kx squared minus 3x plus 6. All right. So the other thing we know is that if we put in the k, so remember we write this as x minus k, so therefore our k is positive 2. So if we put in p of 2, because we know this is a factor, we know the remainder has to equal 0. So p of 2 has to equal 0. All right, and let's actually substitute that in. So we get 2 cubed plus k times by 2 squared. Take 3 times by 2 plus 6 has to equal 0. Again, to the power of 3 is 8 plus 4k. Take 6 plus 6 equals 0. So what we're going to get is these cancel out. We're going to move this to the other side. So 4k equals negative 8, k equals negative 2. All right. Now, the reason we know this, and I should have put it in as I did it, is because of the and I'm pointing to this one here, is because of the factor theorem. So we're always writing down why we know certain things. All right, so k equals -2, meaning we can write this as, therefore, x cubed plus kx squared, take 3x plus 6. That's p of x now. All right, and our final step, because we know k equals -2, we can substitute that in. So p of x equals x cubed minus 2x squared minus 3x plus 6. All right, now we've done that first part, we found k. So now we've got to fully factorize x cubed plus, so we've got to fully factorize it, but that's good because we know what p of x is now. All right, so what we're going to do is, because we've got our polynomial now, and we know all parts of it, and we know that our original our factor of 2 is in here, we're going to do synthetic division, and we're going to pick our k, which is 2, and we're going to divide through by our synthetic division. So the number in front of our x cubed is 1. This will be a good reminder of synthetic division anyway. So 1 minus 2 is in front of our x squared. In front of our x is -3. And then our last number is 6. Okay. So the first thing we did with synthetic division was put in a 0 there. So we went 1 plus 0 is 1. Then we did 2 times 1 is 2. And we just kind of repeated that process. So -2 plus 2 is 0. Then we did 2 times 0 is 0. -3 plus 0 is -3. -3 times 2 is -6. 6 and -6 makes 0. So that's good because we've got a remainder of 0, which we knew we had to. We had to have a remainder of 0. All right. So now what we've got is, we know that we've got our p of x. One of the factors was x minus 2. And the next one's going to be 1x squared plus 0x minus 3. All right. So we've factorized that. So now what we need to do is find a number that, well, you can see that this is the perfect square expansion. You can do this in multiple ways, but one way to do it is the perfect square. All right, because when you see something squared minus something else and there's no x factor, it means that they've cancelled out using the perfect square. So you've got to find the square root of this number, which is x minus square root of 3, and it's going to be multiplied by x plus square root of 3. And you'll see that those, root 3 times x is root 3x. Take away root 3 times x, they'll cancel, and you'll just be left with those outside terms. So we have been able to fully factorize this, and that's what we've been asked to do. So that's how we've had a look quickly at the factor theorem, and hopefully we can do a couple of examples now. Okay, thank you. Oops.